Okay, now let's move to the D and L isomer. So how do we know that this sugar is a D and this sugar is an L isomer? So I have here an example of the one of the simplest monosaccharide, which is a glyceraldehyde. Remember that your glyceraldehyde will the only simplest monosaccharide to have the D and L isomer because it's the only simplest monosaccharide that contains a chiral carbon. So in dihydroxyacetone, there are no D and L in dihydroxyacetone because your dihydroxyacetone has no chiral carbon. Okay, so remember, sugars can only have a D and L isomer if it has a chiral carbon or if it contains a chiral center or that sugar is a chiral molecule. Okay? So example is that you have your glyceraldehyde. Okay. Okay. Reviewing your glyceraldehyde, your carbon number 2 is a chiral carbon. So this contains the chiral center. And the functional group is an aldehyde, which is the most oxidized end. Remember that your aldehyde, review of your organic chemistry, your aldehyde can be further oxidized to carboxylic acid, diba? So you have your alcohol, then aldehyde, then oxidized further to carboxylic acid. So the aldehyde group is the most oxidized end. And carbon number 2 is the chiral carbon. So how do you know if it is a D or an L? By just looking at the OH on the last chiral carbon or the chiral carbon that is farthest from the oxidized end or the most oxidized end. Okay, so this carbon this is the only carbon or this is the only chiral carbon that is farthest to the oxidized end, to the most oxidized end. This one is not chiral, so we cannot distinguish this as the chiral carbon that is farthest to the most oxidized end. Okay, so this is only the carbon that is farthest to the most oxidized end. So to determine that is a D or the L, you look at the carbon that is or the chiral carbon that is farthest to the most oxidized end. Or you can say that it is the last chiral carbon. Okay? It is the last chiral carbon because you can number this as 1, 2, and 3. So the last chiral carbon is on the carbon number 2 because carbon number 3 is not a chiral carbon. So it's either you look at the last chiral carbon or the carbon or the chiral carbon that is farthest from the most oxidized end. Then you look at its OH. Where is it bonded? If it is on the right of that carbon, then that is a D. Okay. If that OH is found on the left, then that is an L. Easy? Yes, it is easy because you just look at the last chiral carbon and whenever the OH is found on the right, then that is a D. Whenever an OH is found on the left, then that is an L. But the D and L is actually not the right and the left, okay? The D there is actually coined because of the optical activity of this stereoisomers, okay? This is actually, the name there is derived from dextrorotatory, which is D, dextrorotatory, okay? And L is levorotatory, that there. So it came from levorotatory. Okay, I will discuss further more on dextrorotatory and levorotatory if we go to the plane polarized light later on. Okay, but remember that term, dextrorotatory, and you have your levorotatory. Okay, I will just put the spelling of that later on. Okay. Okay, let's consider the structure of the glucose. Okay, I will write the structure of the glucose there here. So the glucose is actually an aldehyde monosaccharide. It belongs to the aldehyde monosaccharide group. Okay, so you have here that, and it is a monosaccharide that contains 6 carbons. So it is an hexose, it is an aldose, and at the same time, it is also a hexose for 5 and 6. Okay, it is an hexose. So therefore, combining that, that is actually an aldohexose. Okay, aldohexose. I actually memorized the structure of the glucose, so that's why I can write the structure already. Okay, but if you haven't memorized it, then you can check out the structure of it. Okay, by just research it on a Google. So this is now the structure of a glucose. Okay, this is actually what? The glucose. Why? How did I know that this is a D glucose? Okay, so how do you determine if it is a D or L? Okay, you look at the last chiral carbon. Okay, if the last chiral carbon, if the OH there is found on the right, then therefore that is a D. If the OH there is found on the left, then that is an L. So where is the last chiral carbon? Okay, carbon number 1, is it chiral or not? Okay, carbon number 1. Okay, I will number this first. So you have 6 carbon. Carbon number 1, chiral or not? No. Okay, that is not chiral because it's only bonded to 3 different groups. Carbon number 2, yes, this is chiral. Okay, you notice that this is chiral because it is different group. You have different here, different there, different here, and also different there. Okay, carbon number 3, yes, that is chiral. Carbon number 4, of course, that is chiral. Carbon number 5, yes, that is chiral. Carbon number 6 is not chiral. Okay, only carbon 1 and carbon number 6 is not chiral. 2, 3, 4, and 5 are chiral. Okay? So, where is the last chiral carbon? It is actually found on carbon number 5. And where is OH located? At the right. So, therefore, this is D glucose. Correct? Yes, that is correct. What if that the question will say that find the enantiomer of that glucose or draw the structure of the L-glucose. Okay, how do you make it? How do you write the structure of an L-glucose? Okay, D and L isomer are actually enantiomers. They are enantiomer with each other. Okay, remember how do you define enantiomer? These are non-superimposable mirror images. So in order to find the structure of an L-glucose, since D-glucose and L-glucose are enantiomer to each other, you just put a mirror there. Okay. You just put a mirror there, and those carbon that will mirror to each other are only chiral carbon. Okay, so never mind carbon number 1 and carbon number 6 because they are not chiral. They will never mirror to each other. Only 2, 3, 4, and 5 because these are the chiral carbon. Okay, so how do you draw the structure of a glucose? So carbon number 1 will stay as is. Okay, because that is not chiral. Okay, carbon number 2 is a chiral. So therefore, they will mirror to each other. So you can now find the OH since it is on the right, then you will find it on the left. And the H there. Okay, carbon number 3 is also chiral carbon. Okay, so you will find it H there and you will draw the OH there. Okay, carbon number 4 is also chiral. Okay, therefore, you can draw the OH there and the H here. Carbon number 5 is also chiral. Okay, you can draw the OH there. You can put the OH there and the H here. And carbon number 6 is not chiral, so therefore as is, CH2OH. And now you are done with the L-glucose, which is actually the enantiomer of the glucose. They are mirror images, but they are non-superimposable, and that is what we call enantiomer. Okay, L-glucose, it's because your OH now here is actually found on the left of the last chiral carbon. Correct? That's correct. Okay? Another type of stereoisomer. Okay. So, consider the structure of some monosaccharides below. Consider this structure. When you look at the glucose and the altrose, oh no, let's go first to D-glucose and D-mannose. Okay. When you look at D-glucose and D-mannose, what have you found out? Okay. Carbon number 1, the same. Carbon number 2, they are different. Okay. OH is found on the right while the other carbon is found on the left. Carbon number 3 is the same. Carbon number 4 is the same. Carbon number 5 is the same. Carbon number 6 is the same. So therefore, D-glucose and D-mannose only differ at one carbon only, or one chiral carbon. So what type of stereoisomer does D-glucose and D-mannose have? They are what we call epimers. Okay. So they are epimers with each other. Epimers or epimers. Okay. So epimers are stereoisomers that differ. So they are stereoisomers that differ at only one. So differ at only one carbon only. Okay, one carbon or one chiral carbon only. So they are epimers because they only differ at one chiral carbon only. Okay, now let's take a look at the altrose and the glucose. Okay, let's take a look at the glucose and the altrose. Carbon number 1, yes, they are the same. Carbon number 2, look at carbon number 2. Are they different? Yes, they are different at carbon number 2. They are different at carbon number 2. Carbon number 3, they are also different. Okay. Carbon number 4, they are the same. Carbon number 5, they are the same. Carbon number 6, they are the same. Okay. If there are 2 or more chiral carbons that are different with each other, then they are called what? They are called diastereomers. Okay? D-A-S, diastereomers. D-E-S-T-E-R-I-K-O-M-E-R-S. Diastereomers. Okay. So, D. Okay. Diastereomers. They are called diastereomers if there are already 2 or more. These two isomers differs in 2 or more chiral carbons. Okay? So, therefore, they are called diastereomers. But the main definition for diastereomers is that they are actually non-mirror images. Okay? Non-mirror images, and therefore they are non-superimposable. So they are non-superimposable. Superimposable. Okay, you just write the spelling there in your notebook or somewhere that you can check the spelling. Okay, so diastereomers are actually non-mirror images, non-superimposable. Okay, so all of them, D-allose, D-altrose, D-glucose, and D-mannose, they are actually diastereomers with each other. Okay, so epimers are also diastereomers. Take note of that. That is a very interesting statement. Epimers are or epimers are diastereomers. Epimers can be diastereomers. Epimers are always diastereomers. That is correct. Epimers are always diastereomers. Okay, that is correct. Because both of the glucose and the mannose, they are actually non-mirror images. They are non-mirror images, right? Because carbon 4 and carbon 5 are the same. So they are non-mirror images. And therefore, if you are going to put the glucose over the mannose, they are non-superimposable. Then therefore, they are also diastereomers. Epimers are always diastereomers, but diastereomers are not always epimers. Do you get it? Epimers are always diastereomers, but diastereomers are not always epimers. Why? D-altrose and D-glucose are only called diastereomers, but they are not epimers because how many carbons are they differ? Two carbons, right? Epimers differ only at one carbon. Okay? So therefore, you cannot say that D-altrose and D-glucose are epimers. You can only say that they are diastereomers. That's why diastereomers are not always epimers, but epimers are always diastereomers. Okay? So let's take a look at another example of monosaccharides. We have D-glucose and D-galactose. Okay? So take a look at the D-glucose and D-galactose. Okay, you can say that on carbon number 4, they're actually different from each other. So do you find the difference? Yes or no? They're actually different, of course. And also, our body can also determine that this monosaccharide or this carbohydrate is actually different because our body can only recognize the structure of the D-glucose. Okay? But for D-galactose, it needs to be converted into D-glucose first in order for that carbohydrate to be used up by the body, or in order for that carbohydrate to be used by the body for metabolism. Okay, so that is their difference. Our body can also recognize their difference. If you can recognize them, then our body can also recognize them also. Okay, so D-glucose should be converted first. D-galactose should be converted first into D-glucose to be used by the body. Okay, so carbon number 4 is different here with D-glucose and D-galactose. Carbon number 4 only. So therefore, you can say that they are epimers with each other. Okay? So they are epimers with each other. Are they diastereomers? Yes, of course, they are diastereomers. Remember, epimers are always diastereomers. Correct.